Right. And hello to everyone who watches on the YouTube and reviews the lectures later. Okay, so we start our course on control theory. This, for most of you, will probably, I guess, be the first time you see control theory, the first time you have this kind of course. Is pretty exciting to introduce you to this topic. Control theory is one of those fundamental blocks of robotics, in a sense, kind of similar like how calculus was one of the fundamentals of your education, engineering education or physics education or computer science education in the university. Like control theory is quite as fundamental for robotics as mathematics for for education in general. It's going to be difficult. The topic is not simple, but hopefully we will get through it successfully. So let's start at the beginning. We'll start by trying to very quickly motivate why you would need control theory. We're not going to spend too much time on motivation because it's kind of like, the fundamental nature of the topic kind of implies that you have to, want to go through it. Okay, so what is control theory, first of all? Well, control theory is, in a sense, like a science and method behind controlling things, okay? So we can show you, instead of like discussing theoretical aspects of control theory, we can show you what exactly we control, right, using control theory. Famous examples are like quadrotors, the kinds that are used for aerial photography, videography, etc. All those fancy videos and movies. A lot of inspection, a lot of modern tech, all of it is often done with drones. Another example is industrial robot arms. Also something that we control. So both of those, you cannot do anything with them without control theory, unless someone writes you everything in advance. And all you do is just kind of like use a user interface, which hides behind everything that goes inside, right? The analogy would be kind of like driving a car versus, building an engine for a car, right? Or designing electronics for a car, right? Driving a car, you don't have to understand electronics or mechanical engineering. But if you're going to make cars or even tune cars, you have to understand those. Okay. Right. So people who operate drones or robot arms don't necessarily have to understand control theory. But if you're going to work with them in the sense of making them better or doing anything fancy with them, besides just the use case, basic use cases, you have to understand control theory. Okay. So we can give other examples, of course, modern rockets, such as, you see rockets that, being able to land after being fired to space. That is same as older rockets, of course, but that is just a spectacular example of use of control theory, right? Modern airplanes, both commercial and more agile, smaller ones, they use control theory. Even ships, cargo ships, etc. They, you have to use control theory to an extent there. All kinds of things. But if you see a robot, if something can be called a robot, even remotely, you can expect easily that there will be a lot of control algorithms running inside them. Okay, so that is just examples, right? Everything that moves automatically, you can kind of expect there will be control methods behind those motions. Good. Now, why do we need to study control theory? Okay. So the easy way to answer, at least easy for me, is to say, well, control theory is one of those fundamentals of robotics, right? Same as, let's say, mechanical engineering, electrical engineering, sensing, software development. Control theory is one of those fundamental aspects. Some of people who do robotics will end up doing mostly mechanical engineering. That happens. So some people just spend their career building new robots mechanically, right? Some will spend their career doing electrical engineering and sensing, for example. So some people would mostly come up with new ways of organizing robot sensing. Though this arguably is not even so much robotics as just some general engineering, but that, you know, it's like a field, in which field you work is a philosophical question. Doesn't really matter. You can have a really good career doing those things. Software development, obviously, right? You're studying in Innopolis, you probably expect to do software development. And I would say maybe 80% of the jobs in robotics have to do with software development right now. Much more than with mechanical engineering, for example. At least in the companies that I am aware of. But that said, those are just like aspects that of robotics that become your primary occupation at work, and control theory is one of them. So go to a typical robotics company and you'll find quite a few people who mostly do what you can describe as applying control theory. It's very typical for a robotics person. And if you talk with practicing roboticists, for example, in our robotics center, you'd find that quite a few of them use control theory daily. Not all of them, but quite a few. So it's just one of those things. You have to know it. All right. So this was an easy answer. It was easy because I just reference you to the fact that it is required, for your occupation and so on. All right. Slightly more involved answer could be something like this. When you are going to work on practical tasks, whatever it will be, you're going to just use a robot, you're going to design a robot, or going to write software, etc. You're going to see the same issues popping up. For example, you would see time delays and lags, low control frequency, like not infinite, right? Like finite control frequency in some control loops. You would see that there isn't enough sensory data. Something is not measured. Like you measure position of your joints, not velocity of your joints, so not joint velocities. You would find that the robot is not perfectly rigid. You expect the robot arm to just move like this, but it twists a little bit, just a little bit, but it twists. There is some unexpected dynamics there. You would find that there are some external disturbances, wind, someone banging on the table, and the vibration passes into the 3D printer, and so on and so forth. So you'd find a ton of those things. And unless you know how to orientate yourself in the control theory, you might be baffled by those issues. You'll be like, okay, my robot is not rigid enough. There is some vibration. I have to get rid of this vibration. And then you ask yourself, up to which precision is the magnitude of a 1 millimeter vibration sufficiently small? 1 micrometer, sufficiently small, right? It's you're going to play a game against physics. At some point, vibrations, unexpected dynamics, lags, everything else are always going to be there. So you can make them smaller at using higher costs in production, better sensors, and so on, you're not going to make them zero. So in this sense, this is a game that you cannot win. And it's not going to feel satisfying to play it because you're always increasing the cost. You're always, doing the labors becomes harder and harder. Like, let's say you want to decrease the lag in your sensory system. You want to run everything faster. How much faster can you run it? Make more computing power? Sure. A little bit faster. Less delays for the networking connections? A little bit faster, okay. But, there's a limit. At some point, you'll be like, okay, cannot do any faster. And we still have time lags. So it's not going to be a nice game to play, is what I'm trying to say. Instead, if you understand control theory, you can start to reason about which of those things are a problem and which of those things is not a problem. And you'll be able to see how people who work in the same field reason about those things. When it is important to apply a tool from a theory which addresses the problem, when you don't have to apply anything, when do you have to analyze, and when you cannot analyze. Some of the problems are not solved. And knowing control theory would allow you to quickly understand if what you're trying to do is something that no one did, or if what you're trying to do is something that is obvious and you just need to look up in the textbook. Okay, so basically it is kind of like your professional toolkit. Even if you are not going to be a roboticist, if you are going to just be a mechanical engineer, let's say, or software developer in a robotics company, those are not worst professions. They are extremely honorable professions. But if you're not going to do anything with control theory in your life, you still need to understand what it can and cannot do. Otherwise, you're not going to be able to understand your teammates and their struggles, right? If someone asks you, can we add another sensor to the robot? You need to be able to discuss with them on the same level. Like you need to be able to discuss what we will call observers and observability. You need to discuss how you infer sensory data, like position data, etc., from other sensors, in order to even be able to understand why their need arose, unless you just want to blindly trust them, right? So somehow it's just necessary. It's just necessary to know. Okay, hope I just gave some motivation. It's okay if this motivation is not sufficient. You can just do old-fashioned, do it old-fashioned way, and trust me that I know what I'm talking about. And once you learn the theory, you'll probably be able to form your own judgment on how necessary it is for the robotics. So that is also a possibility. Okay. Now let us just start with the course. But before we do you have any questions? At any point of the yes, go ahead.
Not yet. You gave good motivation, I guess.
No, thank you. At any point when I'm speaking, you can interrupt me, write in the chat, or better still, just unmute and talk. I'll stop and we'll discuss. Because for me, it's very easy to keep on going, and I will be able to go back to what I was saying before you asked. So don't worry about interrupting me. It's easy enough for me to stop, answer, and go forward. So, and we have so few people in this class that you're not going to cause any problems for anyone else. Go right ahead. Like, even in a class with 150 students, we were able to answer all the questions. So in the class your size, no problem at all. So anytime you want to ask something or give your thoughts, unmute and talk. We'll be happy to discuss. All right. Now to the content of the course. So the course will begin with a ton of mathematics. hope to, you'll forgive me. I need to apologize. A ton of mathematics. Mathematics is great, so that's not what I'm apologizing for. I apologize for the fact that we are going to have a lot of repetition of the previous courses, like differential equations and so on. And for the fact that it's not going to be clear what exactly control is until the lecture 3. In the 3rd lecture, it will be completely clear what we do, right? But before that, we need to build towards it. Okay. So let's start building our understanding. So first, let us remember the concept of ordinary differential equations. If you forgot, ordinary just refers to the fact that they are not partial differential equations. So ordinary differential equations look like this. First order ordinary differential equations look like this. So we have here derivative, and here a function of x and t. Okay. So t is usually time. This is usually time. Okay. X is a vector. In this course, I will always denote vectors by bold letters, bold straight letters, vectors. So this is a vector. This is a vector function. This is a vector. Time derivatives will always be denoted by dots, unless it is a derivative of the order 4 and more, in which case it will be, I would denote it something like this. This will be a 4th order derivative, let's say, of x. So this is how fourth derivative of x will be. Right, but normally it will be dots or dt's. You'll see it in a second. Yeah, so this is how what it is, and what it essentially says. What this says is just that we have derivatives on the left-hand side and what they're equal to on the right-hand side. For example, see downstairs, we have x dot equals to minus 3x cubed minus 7. So that is an example of a ordinary differential equation. This is a normal form of ordinary differential equation. We could find all kinds of other forms. For example, you can gather x on the left-hand side, and it will be a different form of a differential equation. But this is a normal form of ordinary differential equation. Okay, so x in this case is usually called state, while the whole thing is usually called a dynamical system. Okay, so it is still ordinary differential equation, but we would often refer to it as a dynamical system. Dynamical system. The word dynamical system maybe rings association if you studied theoretical mechanics. Did you have theoretical mechanics in your syllabus?
We have now.
So you're only starting now.
Yes.
Okay. So but you had physics, I'm sure.
Yes.
Physics. Yeah. Okay. So in physics, you studied second Newton law, right? Second Newton law, most likely in school, even, right? Even in school. So Newton law is an example of a dynamical equation. Basically, it's what is dynamics? It is a study of how accelerations depend on forces. That is what dynamics is. So how bodies and mechanical systems move under the influence of forces. Okay, kinematics is as a alternative field, is the study of how bodies move when you already know accelerations, right? You know accelerations, for example, and you study how the bodies move. In dynamics, we know forces and we study how bodies move. And in statics, you know that there are no velocities, no accelerations, and you just study the balance of forces. Okay. Those are just the main aspects. So that's where dynamics comes from. Basically, why we call it dynamical system, because it relates inputs from the outside, such as forces, to accelerations. In this case, just derivatives like x dot. It will be analogous to our acceleration in physics. Analogous. We'll see analogy soon enough. Okay. So this is a dynamical system, and this is a state of the dynamical system. State is not a word you heard before. So let's think about it for a second. So state of a dynamical system is a minimum set of variables. Minimal set of variables. Very important, the word minimal here. That describes the system. Okay. Minimal set of variables that describe a system. What do you mean by describe? Not clear. So describing means if we know the current state, so x at the current point of time. When I say current, of course, it is just a simplification. We could say if we know x at a point t1, or we can make it t0. If this is known, then, and if we know all future inputs, so all future inputs to the equation, inputs, by inputs we mean, everything else depends on time in the equation, then we can predict the behavior of the system. So what do we mean by predicting behavior of the system? Well, we mean that from that, we can infer x of all other t, right? If you studied differential equations well, you would recognize that this is just a Cauchy problem. So the problem of how to solve a differential equation forward. If you have initial conditions, you should be able to solve the ordinary differential equation forward. I mean, for a class of differential equations, of course. So that is the definition of a state. State is a minimal set of variables that allows you to solve a Cauchy problem, you can say. Meaning that you know it at the initial conditions in terms of the state, you know what it is equal to in the beginning, you'll be able to solve the system forward. So good, but very, very theoretical, not clear what it means in practice. So just examples. For a spring damper system, I hope you remember what a spring damper is, right? Let me, just in case you forgot, let me just illustrate what spring damper is a body. Let's have a chat. Spring and gravity, spring damper. So we have spring, gravity, and damper. But yeah, good. We don't have to have a gravity there, by the way. But I will draw one with gravity just to adhere to the suggestion. So let me just do this one. I will draw a very small spring because otherwise it will take too long to finish the drawing. Okay, this is a spring. And we'll have a damper here. Damper usually has a very specific way of depicting it. So I apologize if my look a little bit ugly. All right, this is more or less how I draw it. What is it? Well, it's a car suspension, the simplest example. Car suspension. So you have a spring, like a spring that's actually just going up and down, and you have some piston here. Inside a piston, you have a viscous liquid. That is just an example of what it is. And it dissipates energy as it moves around. If you ever had a bike with suspension, that is a bike suspension. The idea is that this system would be described by equations such as, I will use double dot like this. I hope you forgive me. This is x double dot mass of the system times x double dot plus dissipation coefficient mu times x dot, okay, plus spring coefficient times x is equal to external forces, in this case force of gravity mg. Sounds good? Like this is more or less clear? Okay, thank you, Yakov. So, and I apologize for writing this way, but if you are familiar with LaTeX, you would recognize this. This is just a way to indicate double dot, right? So, okay. So, this is spring damper. And for a spring damper, the state variables, so the state of a spring damper will be velocity and position. Okay. And that is the state of the variable of the spring damper. Why? Well, because if you know initial velocity and initial position, and you know how external forces act, and external forces in this case is this gravity, you will be able to solve forward. So you will be able to solve the differential equation. And this is true, right? Initial conditions for the second order differential equation. In this case, it will be just x and x dot. That's all you need to know in the initial point of time to solve it. All right. So this is the state of the spring damper. For double pendulum, I'm not going to draw it as elaborately as I did with the spring damper. Maybe just do we have maybe Swiss here? But double pendulum is basically something like this. Right? We have a mass at the end of the pendulum, and we have a joint here. Okay. So for a double pendulum, the states variables could be joint angles and joint velocities. What are joint angles? Well, for example, joint angle can be this angle here and this angle here. Those are joint angles. And joint velocities are just how fast those angles change. So this would be state variables for a double pendulum. You can see that it is more or less just what you need to, again, solve the differential equation forward. So fair enough. Questions about that? Okay. I mean, if you have questions, just ask them. Just go ahead. I will pause and ask you about the questions, but I'm not going to wait for long, but interrupt me if you thought of one. Okay. All right. Now let us move on. Here we have an example of what a differential equation of the nth order or nth degree, I guess, is. So this is a nth derivative of x, and this is a scalar function f of f n-1, n-2, etc., and x double dot, x dot, x t. So x of t, in this case, is the solution to this equation. This, as before, is a dynamical system. And in this case, x, as you can see, it is not bold and indicates that it is a scalar. Like this is a scalar equation. What I showed you right here is a scalar equation. And what is the state of the system? Well, it is not sufficient to know just x to predict future behavior of the system. You also need to know x dot, like, I mean, in some initial conditions in terms of x. You also need to know x dot, you need to know x double dot, x triple dot, this x, and this x. You need all of them to be able to predict how the system will operate forward. Okay. So in terms of initial conditions, you will need to know all of them to be able to predict how the system goes forward. So all of them form a state of this system. Okay. So in this case, it is this set. This will be the state of the system. X, x dot, x double dot, etc. You didn't have to choose it like this. You could choose any other minimal set of coordinates, which will be sufficient. This one is just very convenient. That is all. As long as from your initial state of your state, you can solve Cauchy problem. Everything is good. Okay, so let's just give an example. Here's a dynamical system. Again, scalar, ODE, second order. This is again a normal form. So in the normal form, you have highest order derivative. Highest order derivative is on the left-hand side notice. Okay. In the normal form, highest order derivative is on the left-hand side. Okay. So what is the state variables for this equation 4? So I would propose the state variables here would be x dot and x. I think those would be state variables here. Again, why? Because they would allow you to solve Cauchy problem. Here's another example lower. This is a system of two ODEs, system of two scale equations. Again, normal form. So highest order derivative, in this case, x triple dot, are both on the right-hand side. So now I'll ask you, tell me, what do you think the state of this system will be like? Again, remembering that you should know the state, some initial value of the state, to be able to solve the system forward. It should be the smallest number of variables that you need. So please tell me, what is the state of the system? What do you think?
Maybe x1 dot, x1 double dot, and x2 dot, x2 double dot.
Exactly, absolutely correct. Great.
I have a question.
Yes.
In the example 4, you said that we have to know x and x dot.
Yes.
You mean we have to know x like the function or just the value of x?
So what I mean, we have to know, when I say we have to know, what I mean is, like, definition of the idea of a state is a minimal set of variables, knowing which at some point of time allows you to simulate forward. So when I say we should know x, what I mean, we should know x for some moment of time. So let's say time t equal to 1, we know x is equal to 7, x dot is equal to -3. that is enough to simulate the system forward.
Okay, so we don't need to find the x of t, actually.
We will find it by simulating system forward. So if we know what x is equal to at the point of time, let's say t equal to 1, we will be able to find x to the future. So we'll find x all the way to the infinity.
Mhm.
A Cauchy problem, right? So from the initial condition, simulate forward.
Yes.
So that is what the idea is. But don't worry about it too much. Usually what is state will be very explicitly easy to understand. So don't worry, it's going to be more and more clear as the lectures go on. So
Okay.
right, but I'm glad that here you didn't fall for the trick of forgetting x double dot, x1 double dot. I didn't include it here, but it is indeed part of the state. Absolutely have to have it. So x double dot, x1 double dot, had to have it, and you mentioned it. Good job.
Why we have to have x double dot?
Here,
Yes.
because without knowing what it is equal to, you cannot simulate it forward.
Why? We don't have it in the equation.
That's a good how should I put it? Is a good challenge. I'm not sure if I want to improvise an answer though. So maybe I should have prepared an answer to this question. Should have anticipated it. But simple answer would be like this. In order to, I guess I can improvise an answer. In order to know how x dot changes, you need to know what x double dot is. Okay. So in order to know what x dot, x1 dot will be like next moment of time, you need to know what x double dot is. So let's say x double dot is equal to 100. x1 is going to change very fast. Let's say x double dot is equal to 0. x1 dot is going to change very slowly. Okay, big difference. And that is why, in order to solve it forward, you need to know what x double dot is. It's initial as an initial condition. Later, you will be able to know what it changes into based on this expression. But you need to know what it is initially. So I guess that is the answer.
Difficult answer.
Yeah, not easy. But if this somehow feels a little bit mathematically not clear, as in if it is linguistically unclear, don't worry, it will be clear soon. If it is mathematically unclear, need to revisit Cauchy problem. So how to solve ODE from initial conditions. But that we'll have in a practice session too. So you'll be covered today. It's by the end of the seminar. So, don't worry, you probably won't even need to go to textbook on differential equations. It'll be reviewed in the class.
Good.
Good. Thank you for the question, guys. It's very good. So let me continue. Now, linear ODEs are different from ODEs in general in the fact that x, so those state variables, x, will only enter into the equations as linear in a linear fashion. So only as the right-hand side will be a linear function of the state, like this. So expression 6 is how linear ODEs look like. Example of linear ODE is like this: x1 dot is equal to minus 20x1 plus 7x2, x2 dot equal to 10.5 x1 minus 3 x2. That is an example of a linear ODE. Okay. We don't have to write it as a system of equations. We can write it in a matrix form. So like here, we have a vector of derivatives, x1, x2, x3 is equal to a matrix, right? This matrix here, times a vector of states. So we have our vector of states multiplied by a matrix, you get a vector of derivatives. You can see if you open the brackets, you would get a system of equations back, right? So equation 8 is can be represented as a system of equations. System 7 can be represented as one matrix equation. Right? Just two ways to write linear systems. You couldn't do it necessarily with non-linear systems. Like this is this is very typical linear systems way of representing things. But for non-linear systems, it doesn't work most of the time. Okay. So linear equations. That's again a normal form of linear equation. Now, we can have a, not a first order ODE. This was a first order, right? First order meaning derivative is 1. So x dot, that is the highest order derivative. We can have a single ODE, but in a higher order ODE, right? Doesn't have to be first order, right? We can have nth order ODE. So if we are thinking about single ODE of the nth order, it is quite customary to write it in this fashion. Notice here we collected all the x's on the left-hand side. That is different from before. So we collected all the x's on the left-hand side. People often do it. So just trust me, that is very typical. In this case, you can still identify what you can designate as a state. For example, this equation 10, the state can be x double dot, x dot, and x. You can call it state of the system. But you can see it is now, everything is on the left-hand side. That form, I think, shows off that it is homogeneous equation. I don't know if you remember those terminologies. Homogeneous means you only have x. So x, but triple dot, x double dot, x dot, x, but nothing that is not x. Okay, that is why homogeneous. Here is another example. Here is the state variables will be x dot and x. And still again, everything's on the left-hand side. This form of equations is actually what we are going to see most often in the course. This one, together with what we saw on the previous slide, this one. So this will be very typical for first order equations. And for higher order equations, very typical will be this. Okay. All right. Hope no one is scared yet. Anyway, linear equations. So the simplest ones of differential equations that we saw. Good. Now, here comes control theory for the first time. All of that we saw before was mostly just, differential equations. Maybe the word state was new. Everything else was from the course on differential equations, I think. Now the first word that is specific to control theory, I think, and that is input. So differential equation can have an input, okay? Can have an input. What is an input? Well, here, this function of time, u of t, we will call it an input. Input can be one of many things. For example, this can model control input. What is a control input? Well, since you are robotics students, maybe you already thought about how robots operate. Maybe you even build a robot. Maybe you had a drone. Imagine a motor of this robot or a drone, and there is a voltage that comes in. So this voltage, you can think of it as control input. If you are more familiar with thinking about robots in terms of torque, like in terms of mechanical aspects of the robot, so you think, oh, this motor produces some amount of torque. Well, torque would be control input to the mechanical structure of the robot. Okay. Maybe you are more familiar to using drones where you have a joystick and you just kind of move around your, what do you call it, controls on your joystick. Well, the signals that your joystick sends can also be control input. So it is just a function of time that you don't attempt to find out from the dynamics itself, that comes from the outside somehow. That is typically control input. That is one way how we can use U. Another way how we can use U is to model external forces acting on the system. Let's say you have wind, and you want to understand how wind changes the behavior of your system. Or you can put wind here. It can be something else. It can be like, for example, a person comes up and shakes your robot, and you want to understand how your robot will react. You can put this shaking force here. Can be all kinds of other things. So that is the idea. Some external disturbance, external force. Good. Also, sometimes, and we will find it very soon, we like to substitute here just some specific force profile, and study the behavior of the system using this force profile. For example, very often we substitute sine wave, or step function. What is sine wave? You already know, sinusoid, right? Step function, on the other hand, I mean, it's also simple enough. Well, give me a second, I will show you. So a step function, if you have two axes, right? And step function would be typically something like this. Where very typically it is as, the height is 1, that is customary, and it starts at the point 0. So this is a typical step function. It is 0 before, so before the point 0 it is 0. After the point 0 it is 1, and it is 1 until infinity. So this is a step function. And a reaction to the step function is a very typical way to analyze a system. We call it step response. We'll study it later, but is very typical, and that's what that is another way to use U of t. So input can be a lot of things. It can model something that you do to the system, can model something that someone else does to the system. It can be just used to study the system. So that's what input is. But this is one of those moments where you have to kind of like fight your desire to use previous conceptions. From differential equations course, you have an intuition that this is just a function of time. You don't like the idea that I call it input, probably. So you have to fight it. It is kind of like the same idea of how when you first see like this, oops, where do I write? Yeah. When you first see this, right, in programming, you fight against it because this doesn't make sense to you since you were learning algebra before. But then you understand that it's not algebra, this is memory manipulation, and then you understand what we do. Same here. I understand you desire to fight against this being something more than just a function, but allow it to, allow the word input. Just allow it. It'll be good. So, okay.
So may I clarify something?
Yes, of course.
First of all, we like our state, the initial values for our state, we don't take into account any input. And then we say that this state equals to this input. I just don't understand it because for me, it feels like the input has influence on the state. And here we say that they're equal. I don't understand that.
What do you mean they're equal?
We have equality sign. I mean, don't we take into account this input in the parameters like A2, A1, and A0?
A2 and 1 and A0 are just numbers. So
yes, like they are some parameters.
Numbers.
Like mass or something.
Yes, exactly.
Yes. So when we so then why don't we say that mass is the input?
Mass is not like mass can be an input. If you, for example, have a cargo ship and someone loads it with continuous mass, like you pour coal, for example, on the cargo ship, mass can be an input. But for example, for a drone, the mass stays the same throughout the whole flight. You can call it input, but it doesn't make sense. Good question. So we don't usually. Input is not a physical property of the system. Input is not a mathematical object. It is just a way to call something, a convenient name, which we'll use a whole lot. So it's just a name, very convenient, but it is not a mathematical object. It's very important. Mathematically, it is still a function of time, just a function of time. And you know exactly how to solve this type of equations.
Okay.
So mathematically, nothing changes. It is just that I ask you to, when I write u of t, and input variable will be almost always u of t. Sometimes will be different, but u of t is a very typical way to designate input. So just keep in mind, this is not some random function of time. It is also somehow input. Okay, that is all I'm asking. Okay, so linguistical stuff, not mathematical stuff. Good. Any more questions? Okay. Now that is input. Okay. So we can write equations with input in general, like this. This is a very typical way of writing equations with input. And we can write equations with input as a first order ODEs, like this. So this is also very typical. This is a typical way to represent a first order ODE. Okay. Now, I'll like to point out, I'll point it out a few more times during the course, but here, U is bold, it means vector. V is bold, B is bold means a matrix. A is bold, and matrices are big capital letters. both normal letters are vectors. Right. So I write it this way because typically we have B is typically matrix, U is typically vector. But strictly speaking, if you want to represent this equation in this form, U will still be a scalar and the B will be a vector. So, but this is okay. This is not a big problem. It's not going to lead to confusion, so don't worry. If you start to transform this into this, you will see the shape of B and U. So you're not going to be confused. But this is very typical form of a linear system. So this is, you're going to see it until the end of the course. This equation will be on every slide, I'm pretty sure, on every lecture. Okay. Okay. So far, I think this one maybe is more confusing for you because you haven't seen those very often. But we'll see them soon enough. All right. Right. So this is equations with inputs. Those equations with inputs. Equations can also have output. If input wasn't confusing enough, we can add an output to the equations. So output. Output is same as input, not a mathematical concept, and it doesn't have a single interpretation. There are two very big interpretations for the input. Okay, for the output. Sorry. And it depends always on the practical use case, but very typical interpretations are as follows. What we measure, that can be output. So what we measure. And another one, what we care about. Okay. Care about means want to control. Just as an example, let's say you have a drone. If output is what you care about, maybe it is your position, X, Y, Z of your drone. That's what you care about. You want it to be right here, sitting there, like where you ask it to sit. Okay. Maybe also you care about its orientation, your orientation, if you have a camera on the drone. That's what you care about. If your drone has a rotating camera, maybe you don't care about your. Okay. Now, what you measure for a drone can be something completely different. Velocities, for example, height, for example, and maybe X, Y position using GPS. So it would be, let's say, based on GPS, you get X and Y. Maybe you get height, maybe also based on GPS, but height is usually relatively difficult. I don't want to comment, but height for drones is maybe a separate issue. You would get angular velocities, and you might, and that's it, right? That's it. So you get different sets of signals. So they are not the same. Basically, output is so either what you measure or what you want to control. All right. So output is usually denoted as Y. Is very typical almost everywhere. Y is usually output, and we can write it as a function of the state. So usually output is a function of the state. It is like g of x. Can be function of input as well, but that is rare. So we're not going to touch it in this course. Okay. Now, state space representation. I think maybe that's the first time you saw this word. State space representation, meaning a representation. It's basically this representation, right? Of systems with input and output. looks like this. Okay. So this guy here, that is called state space representation. We have here input u, input u, output y. And that is our state space system. So if u is scalar and if y is scalar, so there's one input, one output, and you want to represent the system as a single ODE. So something that you have been studying in your ODE course. Then what we often do is we take this output and we use it as a variable for the ODE. So we try to rewrite, now it's a little bit difficult what I'm trying to say, but no, bear with me. We try to rewrite this thing in this form. So we go from there to there. And one of the aspects of this rewriting is that we use the same y here and here. Well, it's typical. I'm not saying this is the only way. There are many ways to go from one to another. But one of the ways, if you have a single y and single u, you can do this. You can do it almost always. It's just that when you have this situation, single u, single v, it's pretty typical to be able to go from one to another like this. And this is one of those practical things that we'll do in the course. Okay. Of course, this u will be the same as this u. All right. How to do it? I will show at the end of the lecture, if we have time. Okay. Now, so in this course, what we are going to study will be usually this type of equation and this type of equation. Those two, what is going to be what we are studying. This one is state space representation. So this is a state space representation. When I refer to this one, I will just usually call it ODE, linear ODE, or something like this. So what is good is that if you have this guy, it's actually very easy to go from it to this guy. So as long as we know how to work with this equation, we'll be able to work with this equation for free because of this transformation. Okay. So you want to work with the equation 17, but you only know how to work with equation 18. Well, good news is equation 17 can be transformed to 18. And in fact, most software prefers equation of the type of 18. So this transformation will be very typical. Very typical. Let me show you how it's done. Let me show you how it's done. So now, please pay attention. Technique that I'm going to show you is going to be everywhere. Homework, classwork, assignments, exam, everywhere. So this technique, one of those things you have to know. All right. So consider equation. Equation q triple dot or y triple dot a2 y double dot a1 y dot a0 y equals to u. Okay. We want to transform this equation into a state space. So we want x, what we want is basically x dot equals to ax plus bu. Okay. Let me first propose a change of variables. Change of variables here. X1 will become y. Okay, x1 will become y. X2 will become y dot, and x3 will become y double dot. Okay. Why did I do this? Well, I can. So there is nothing wrong with it. I can always choose a variable x1 to be equal to y, x2 to be equal to y dot, x3 equal to y double dot. There is nothing mathematically that I am breaking here. So I can do it. That is all, right? So let me write it into, write it here as a system of equations. And let me differentiate all those three. So let me differentiate the first one. What I get is x1 dot is equal to y dot, right? I'll get x2 dot is equal to y double dot because differentiation, right? And x3 dot will be equal to q triple dot, y triple dot, which is the same as this guy, right? Okay, so q3, x3 is equal to q double dot, x3 dot will be equal to y triple dot, which is, here's what it is. Very easy to express it from here would be u minus a2, a1, a0, right? All of this. Okay. Now comes interesting part. Let's look at the first equation here. Okay. x1 dot is equal to y dot. But y dot, we know that it is x2 because we just introduced this notation. So in fact, we have this relation, okay, from here. Okay. So we know that x1 dot is equal to x2. Based on our notations that we introduced. There's nothing profound here. It's quite obvious if you think about it. If x2 is equal to y dot and xy is equal to y, of course xy dot will be equal to x2, right? Makes sense. Same here, x2 dot is equal to q double dot, or y double dot, sorry. But y double dot is equal to x3. So y double dot is equal to x3. So we have x2 is equal to dot is equal to x3. And finally, we can use here, we can notice that this guy is also x3, right? We can notice that this guy is x2. And we can notice that this guy is x1. So we have the system of equation. X1 dot is equal to x2, x2 dot is equal to x3, x3 dot is equal to u minus x3, a2 x3, a1 x2, a0 x1. And we can rewrite this whole thing in this way. Okay. So we how did we do it? Well, if we collapse this back, like multiply it back, you would see x1 times 0 plus x2 times 1 plus x3 times 0. This gets us here. Here it would get us this times this will be equal to x2. So it will be this equation, right? Good. Yes.
May I ask a question?
Yes.
I do understand it mathematically, but we said that x is state, right?
X in this case, the state will be x1, x2, x3.
So
all three.
Just substituted output with the state. Is it like physically correct?
There's nothing physical about the words state, output, input, etc. So just don't worry about it. Is like we're not doing metaphysics here, right? So the words, they may be confusing for a while. Give it a few lectures, they will stop being confusing. For now, like this, what we do here, you have to understand the mathematics, okay? When we finish, we can look back and what we have done, and then we can ask, does it make sense? What's the state? What does it mean to be a state, output, etc.? So, what you're asking is a good question. Actually, it's just that I'm afraid to start discussing before we finish mathematics.
Okay.
No, but good question. So here, when we multiply this by this, notice what will happen is we'll get x3. So this guy. Okay. And when we multiply this by this, what will happen is this guy. And finally, this thing is just u that happens to be here. So this is how we get to this beautiful form from our initial equation. So let me just so this is how we do it. So our initial equation again was this. We got this using this transformation. Okay. Questions about mathematics? No questions about mathematics. Okay. Now, let me just see, do we have a continuation for this? No, no continuation. So let me explain what those matrices are. So this matrix is matrix A. So this is matrix A. Okay, this is matrix A. We don't have matrix B here, but if we wanted to write matrix B, because this is not matrix B. Like what we see here is just something. It's not a matrix B. So if we want to write matrix B, it would look like this. It will be plus let me 0, 0, 1. That's how it would look like. The vector thing. Apologize for writing so slow. It's difficult in Zoom. This will be, and then this thing will be matrix B. Okay. So we could have rewritten this guy in this form, and this 0, 0, 1 would be matrix B. Okay, that's if we wanted matrix B. Okay, now what if we wanted matrix C? So output, right? There was a really good question about our output, what output is here, and why we have output Y here. Very good question. So let me just show you how we could potentially do it. So we know how output relates to the X here. Here we already have this relation. This is how output relates to X. So we can rewrite it in terms of vector X as Y. Let me change color here, maybe to reflect this. Y would be equal to 1, 0, 0 times X. Here I understand X as a vector, right? So just to illustrate, like this would be, wait a second. This would be X. This is X. So y would be equal to 1, 0, 0 times x. And this would be, this matrix here would be C, the C matrix. Now, we had the question. The question was it correct to, we had this output and we call it a state now. Was it correct? That sounds wrong when you say it like this, right? But let me say the same thing, but in different words. Can we call x1 part of the state an output? And here you can say yes, of course. Let's say x1 is the position of your spring damper, or better still, is the position of the what would be a good example? Because it is a third order system, so I cannot use a very simple example. Well, I'll abuse the terminology a little bit here. Let's say X is the position of your spring damper system, position of your spring damper system is a state. Does it make sense to call it an output? Yes, of course. Of course, it makes sense to call it an output. If we care about position, if we want to control the position, that is an output. Sure, of course. Does it make sense that our differential equation here is written in terms of the position of a spring damper? Yes, of course, it makes sense. That's position variables is the most typical way we write equations in. Okay. Does it make sense to, yeah, so would it make sense to have something else as an output, like velocity? Yeah, sure, no problem. So there is no problem that one of the state variables is an output. It is just that you know, change them, like change sides, and it stops being so weird. It's not that you're making output into the state. It is that you recognize that this output was a state. That is more philosophically correct, but ultimately is just language, and we're doing like, you know, ultimately we're doing math, so don't worry too much about the language. Hope it helps. Do we have more questions about this transformation? All right, we'll have this also in recommended reading material, so you will be able to review it with the different reading material as in the lecture. So we'll also have it in practice, so you would have time to practice it. Now, we have how much time? No time, or a couple minutes? Let me see.
8 minutes.
8 minutes. Okay, good. So I'll use that means to just show you something more advanced that is not necessarily going to be on the test or on anything, but I'll just show you something that is, I think, is satisfying. So let's say we want to go from this to this. Oh, sorry, to this, right? This is the same thing. It's just I rewrote this guy in terms of scalar variables. And I want to go back to the second order differential equation. You can imagine why you would want to go to the second order differential equation, because this looks huge. This is so small, so compact. So makes sense you would want to go from here to here, right? Okay, so how to go from state space to ODE? We need to, yeah, so we just want to rewrite this as an ODE. We need to remember that initial conditions of both equations will have to agree. So that is just some aspects that we need to remember. All right, good. How to do it? So we know what y is, right? Y is Cx. Okay. So y dot will be equal to Cx dot. Okay. So since y is Cx, y dot will be Cx dot. All right. but x dot is equal to ax. So that's why we can rewrite x dot as ax. And we know that y dot is equal to cax. Okay. Now we can open this expression like this. In particular, we can multiply them by each other. We will get this. I just did multiplication for you, but you can verify that's what we will get. Okay. We didn't have to open it, but it's just kind of interesting to see. Okay. Now we can also find what q double dot will be like. It will be CAA. Okay, why CAA? Well, q double dot will be equal to CAX dot, because C and A are constants. So when you differentiate, you would get extra dot here, and X dot is again. So when you add an extra dot here, you will replace this guy with this guy. That's how you get extra dot here. Okay, so this is just basically this differentiated gives you this. That's the idea. All right. So now we know what x is, y is, what y dot is, and what y double dot is. Good. That's what we found so far. And it wasn't very difficult. Now, combining results for y and y dot, we can write this huge expression here. We say that y and y dot are equal to this huge matrix here times x1, x2. Okay, y and y dot are linear functions of x1, x2. Again, the first equation is just y equals to c times x. The second equation is y dot equals to ca times x. So that is all. So this huge matrix is a transformation matrix, which we can use to express what x is in terms of y. And x is t minus to the t inverse times y dot. Okay, that is what x is. T inverse y times y dot. Okay, that's what x is. Now we know what x is, and we know what q double dot is. Okay, so q double dot is CAAX. Remember, we got it by differentiating twice. But we know what x is. X is t minus 1 y dot. So we just substitute, and we get this whole thing. And that will be your equation. When you open this matrix here, when you open this up, it will be just two coefficients. It will be two numbers. The first one will be coefficient in front of y, the second coefficient in front of y dot. It looks scary, but ultimately it's a square matrix times square matrix times square matrix times horizontal vector. Okay, matrix of two elements. Easy. I mean, multiplications are going to be easy. The process is also if you do it on a computer. And that's how you go from a state space to ODE in the case when y is scalar. I didn't show you inputs. I didn't show you where u goes, but you can guess based on how I did it with everything. You can, do it yourself. Add u, scalar u, and see how you add it here. Is a good exercise. Okay, Yakov approves in the chat. Thank you. All right, so this is it for how to do this particular transformation. As you can see, it's not so difficult, but it is nicer to do in MATLAB or Python rather than by hand. Okay, so if you want to check it out, you'll be able to check the code here. This is last year's code. So it will be linked directly to a Colab page. Now, here's the recommendation. Those two are MIT handouts. They're very big, and they cover a little bit more than the first lecture. They, in fact, cover material for the lecture 1 and a little bit of the lecture 4 and 5, mostly 1 and 4. So there will be a little bit of material for lecture 1 and a little bit for lecture 4, because their course is not structured the same as ours. But very useful. You can start reading. You can just, you'll be able to find essentially the materials that we covered here, especially like this one. In the beginning, it would just expound on what I was discussing. Okay, this is a different take on the same material. So if you want, you can see differential equation to state space. It even says state space representation of linear systems. So is again different take on the same stuff. If what I explained is not clear, try listening to them or reading them as PDFs. You'll be able to find something good. So I'm not sure if this repository is public yet, but it will be public by the end of the day. I will send the link in the chat. But essentially, in every class, we'll be able to just, at the end, you can scan the QR code. You'll be able to go to the GitHub page and see the book recommendations, see the slides, and everything else. So that's how we are going to keep it updated for the course. That is it for the first lecture. Thank you for sticking out until the end. Do you have any questions?
No, everything was clear.
It's very good. I'm glad. Right. Thank you, guys. We'll see each other next week. But make sure you attend to the next two classes too.
Thank you. Goodbye.
Bye-bye.